Hello, welcome to our Milestone 2 presentation. We are Team 4, and my name is Sai, and I'm here with my teammates Marta and Robin. First, let's start with our linear regressions.
We began the linear regression work by defining the individual features for each run and our dependent variable GHG emissions per capita. Then we split the data into training and test sets and fit the model. We then took measurements of the intercepts and coefficients for the training set. For both our intercepts and coefficients, we found a wide range of values, including both negative and positive values. After further analysis, we were able to conclude that most of our individual features were weak predictors for our dependent variable. We found that our two most predictive features are GDP per capita and total final energy consumption per capita. When creating residuals plots, we were able to observe that the majority of our plots were curved up and had upturned outliers on each end. The residuals plots for GDP per capita and total final energy consumption per capita were almost entirely straight, with some outliers on the right tails of each plot. As a result, we were able to conclude that the use of a linear regression model was likely only appropriate for these two features. We then made a prediction set and plotted the results with their confidence intervals and prediction bands. Most plots appeared very similar to the scatter plots of the training data, with regression bands, indicating the prediction sets were relatively accurate most of the time. We also found while measuring the correlations that GDP per capita, energy intensity level of primary energy, population total, access to electricity, percent of rural population with access, and total final energy consumption per capita had the strongest correlations between predicted and real values. While measuring the mean squared errors, we found that the features that produced the lowest MSEs were total final energy consumption per capita and GDP per capita, indicating that the model was the best fit for these features. Then we moved on to multivariate regressions. We created 4 combinations of variables and measured their coefficients. The first 3 were composed of different combinations of the most predictive individual features, and the fourth was a combination of all of the features. After further analysis, we concluded that the most predictive features were total final energy consumption per capita as a strong predictor, GDP per capita as a moderately strong predictor, total electricity output per capita as a moderate predictor, and access to electricity percent of urban population with access as a weak predictor. We found that combinations 1, 2, and 3 had strong positive correlations between predicted and real values, and combination 4 had an extremely strong positive correlation. Combination 4 and 2 held the lowest MSCs of all the combinations, indicating the model was the best fit for these groupings. Our last step was rerunning our models with regularization. For the individual features, we found improvements made using both the lasso and ridge methods for fossil fuel energy consumption, energy intensity level of primary energy, renewable electricity share of total electricity output, renewable energy share of TFEC, population total, and total electricity output per capita. We found improvements made with just the ridge model for access to electricity percent of rural population with access to electricity percent of total population, and access to electricity percent of urban population with access. For combinations 1, 2, and 4, we saw improvements with both the lasso and ridge methods. For combination 3, we saw improvements with just the ridge method.
The next step of our project is the logistic regression classifier. Since logistic regression classifiers best predict the outcomes of a binary event, we first had to convert our target variable, greenhouse gas emissions, from a continuous variable into a categorical variable. To do this, we set a standard 3.5 tons carbon dioxide as our binary value, meaning values that are below 3.5 would be converted to a 0, and values that are above 3.5 would be converted to a 1, signifying a low and high emission class standard. We created another column called binary class and populated it with zeros and ones using this criteria, and set that as the target variable for our logistic regression classifier. Then we split our dataset into a training and test set. Based on the results of our multivariate regressions from before, we found that the combo number 4, which is the combination of all independent variables, is the best predictive combination. Using that, we used all independent variables in this classifier. This is the resulting intercept and coefficients from that. And as you can see, the coefficients cover a wide range covering both negative and positive values. These are the log odds and odd ratios of the outcome for a unit increase for each independent variable that we used in this classifier. As you can see, values that like and agricultural land and energy and electricity consumption variables have the highest log odds, indicating a more stronger relationship between the variable and the resulting outcome, while the odds ratio is also a greater value for those variables too, which kind of matches with the expected values for these variables. Using this data, we then found the most predictive features according to the training data set. The top three are total electricity output per capita, GDP per capita, and total final energy consumption per capita. Two of those match up with the same results that we got from the linear regression classifier as being the most predictive. Finally, we used the trained logistic regression model to make predictions on the testing data set and calculated the accuracy of that prediction, finding that the logistic regression classifier was actually achieved 99% accuracy. The next step was the naive Bayes classifier. Using the same training test split, we created and trained the naive Bayes classifier and made predictions on the test set and generated a confusion matrix to interpret the results. As you can see from this matrix here, the naive Bayes classifier was most accurate for guessing the higher emission standards, meaning a value of 1 in the binary class target column. We repeated the same experiment, but this time adding Laplace smoothing with a value of 1 to see if that would improve the results. However, the resulting matrix is identical to the previous one, indicating no improvement by adding the Laplace estimator.
In this section of the presentation, we'll go over the decision tree and random forest method for training our model. Starting off, we had to split our data set into training and testing, and we used an 80-20 split. And subsequently, we had to verify whether the distributions were similar after making the split. And so we used histograms to plot the distribution of the total electric output, and we can see that the training resembles the testing distribution, and similarly for the distribution of the agricultural land, and we can see that effectively our distributions are similar after making the split. To effectively train our decision tree model using the if-then method, we created three classes based on the GHG emissions, ranging from low, mid, and high. The low ranged from 0 to 1.5 tons of carbon dioxide equivalent, mid ranged from 1.5 to 6 tons, and the high was anything above 6 tons of carbon dioxide equivalent. As a result, this was the decision tree that was modeled based on our classes. And we can see that we have three pure leaf nodes, which makes it easier for the model to effectively predict the GHG emission level ranges within a few branches of the decision tree. After effectively creating our decision tree model, we performed a confusion matrix to understand the strengths and weaknesses of the decision tree model. We were trying to identify if there were any misclassifications with our decision tree. However, we found that in fact our decision tree was performing very well, as we can see in the results of our training and testing accuracies, meaning that it was effectively classifying our GHG emissions in the three categories that we have defined. The next step was to use gradient boosting to see how an increased number of decision trees would effectively affect our predictions, and we can see that our model remained fairly accurate by increasing the number of trees. And similarly, when we performed bagging, we used a range of trees from 50 to 200, and we can see that our testing data set remained accurate even with an increased number of trees using the bagging method. Lastly, we use random forests to make predictions towards our model. We started off using an 80-20 split, and we can see that by increasing the number of trees, the accuracy remained the same, and it was able to effectively predict the different ranges from low, mid, high of the GHG emissions. However, when we change the split to a 60-40 as well as a 50-50, we see that as we increased the number of trees, our predictions actually decreased up until we reached 100 trees. At that point, we reached a threshold where if we even increase more trees, the predictions remain relatively the same. Lastly, the features that were most important. At number one, we had the GHG emissions per capita at about 66%. And secondly, we also had the total electric output per capita at about 18%. So those were the two features that were most important for our model. And in fact, that makes sense as the GHG emissions were important in order to classify whether it was low, mid, or high.
In summary, if you look at the results of our project, linear, logistic, and decision tree classifiers have their own distinct characteristics and applications that you have to compare and analyze to see which ones is the best options for us. Linear regression is primarily used for predicting continuous numerical values, and it works well when there's a linear relationship between the independent and dependent variables. However, it's not suitable for classification tasks or when the relationship is nonlinear. The kind of linear relationship that is necessary was mostly absent between our independent variables and the greenhouse gas emissions column, except for two specific variables. But just the fact that our target variable is a continuous one makes it the most ideal option on paper. Logistic regression, on the other hand, is specifically designed for binary or categorical classification tasks and predicting the probability of an event occurring. Performs well when the decision boundary between classes is linear or when you're dealing with categorical data. And again, our target variable is continuous, depicting the emission rates per capita. So it required us to make a separate binary column. And once it was created, though, it was highly accurate at 99%, showcasing the strength of a logistic regression. So when you compare the both of them, overall, although linear provided a weaker correlation between most individual variables in the target, the multivariate regression was promising as two of the combinations provided a very high, strong correlation and great predictive quality in terms of the testing set. Decision trees, on the other hand, are versatile algorithms capable of handling both regression and classification tasks. They first partition the feature space into regions based on feature splits, and it can capture nonlinear relationships and interactions between variables, making it very useful for more complex data sets. In our case, we found that it provided highly accurate results, in fact, 100% accuracy, but caution is needed because decision trees are prone to overfitting, although they can be mitigated by using random forests and increasing the number of trees. Although our results showed how the number of trees stopped really making any difference once you got past around 100. And that is all for our presentation for Milestone 2. Thank you for listening.